Nitrous oxide, commonly known as laughing gas, nitrous, nitro, or NOS, is a chemical compound with the formula N2O. It is an oxide of nitrogen. At room temperature, it is a colourless, non-flammable gas, with a slightly sweet odour and taste. It is used in surgery and dentistry for its anaesthetic and analgesic effects. It is known as laughing gas due to the euphoric effects of inhaling it, a property that has led to its recreational use as a dissociative anaesthetic. It is also used as an oxidizer in rocketry and in motor racing to increase the power output of engines. At elevated temperatures, nitrous oxide is a powerful oxidizer similar to molecular oxygen. Nitrous oxide gives rise to NO on reaction with oxygen atoms, and this NO in turn reacts with ozone. As a result, it is the main naturally occurring regulator of stratospheric ozone. It is also a major greenhouse gas and air pollutant. Considered over a 100-year period, it has 298 times more impact per unit mass than carbon dioxide. It is on the World Health Organization's list of essential medicines, a list of the most important medications needed in a health system. Applications: rocket motors. Nitrous oxide can be used as an oxidizer in a rocket motor. This has the advantages over other oxidizers in that it is not only non-toxic, but also, due to its stability at room temperature, easy to store and relatively safe to carry on a flight. As a secondary benefit, it can be readily decomposed to form breathing air. Its high density and low storage pressure enable it to be highly competitive with stored high-pressure gas systems. In a 1914 patent, American rocket pioneer Robert Goddard suggested nitrous oxide and gasoline as possible propellants for a liquid-fueled rocket. Nitrous oxide has been the oxidizer of choice in several hybrid rocket designs. The combination of nitrous oxide with hydroxyl-terminated polybutadiene fuel has been used by Spaceship One and others. It is also notably used in amateur and high-power rocketry with various plastics as the fuel. Nitrous oxide can also be used in a monopropellant rocket. In the presence of a heated catalyst, N2O will decompose exothermically into nitrogen and oxygen, at a temperature of approximately 1300 degrees C. Because of the large heat release, the catalytic action rapidly becomes secondary as thermal autodecomposition becomes dominant. In a vacuum thruster, this can provide a monopropellant-specific impulse of as much as 180 s. While noticeably less than the ISP available from hydrazine thrusters, the decreased toxicity makes nitrous oxide an option worth investigating. Nitrous oxide is said to deflagrate somewhere around 600 degrees C at a pressure of 21 atmospheres. It can also easily be ignited using a combination of the two. At 600 ASI, for example, the required ignition energy is only 6 joule, whereas N2O at 130 ASI would not react even with a 2500 joule ignition energy input. Specific impulse can be improved by blending a hydrocarbon fuel with the nitrous oxide inside the same storage tank, becoming a nitrous oxide fuel blend monopropellant. This storage mixture does not incur the danger of spontaneous ignition, since N2O is chemically stable. When the nitrous oxide decomposes by a heated catalyst, high-temperature oxygen is released and rapidly ignites the hydrocarbon fuel blend. NOFB monopropellants are capable of ISP greater than 300 seconds, while avoiding the toxicity associated with hypergolic propulsion systems. The low freezing point of NOFB eases thermal management compared to hydrazine and dinitrogen tetroxide, a valuable property for space-storable propellants. Internal combustion engine. In vehicle racing, nitrous oxide allows the engine to burn more fuel by providing more oxygen than air alone, resulting in a more powerful combustion. The gas itself is not flammable at a low-pressure temperature, but it delivers more oxygen than atmospheric air by breaking down at elevated temperatures. Therefore, it is often mixed with another fuel that is easier to deflagrate. Nitrous oxide is stored as a compressed liquid. The evaporation and expansion of liquid nitrous oxide in the intake manifold causes a large drop in intake charge temperature, resulting in a denser charge, further allowing more air-fuel mixture to enter the cylinder. Nitrous oxide is sometimes injected into the intake manifold, whereas other systems directly inject right before the cylinder to increase power. The technique was used during World War II by Luftwaffe aircraft with the GM-1 system to boost the power output of aircraft engines. Originally meant to provide the Luftwaffe standard aircraft with superior high-altitude performance, technological considerations limited its use to extremely high altitudes. Accordingly, it was only used by specialized planes like high-altitude reconnaissance aircraft, high-speed bombers, and high-altitude interceptor aircraft. One of the major problems of using nitrous oxide in a reciprocating engine is that it can produce enough power to damage or destroy the engine. Very large power increases are possible, and if the mechanical structure of the engine is not properly reinforced, the engine may be severely damaged or destroyed during this kind of operation. It is very important with nitrous oxide augmentation of internal combustion engines to maintain proper operating temperatures and fuel levels to prevent pre-ignition, or detonation. Most problems that are associated with nitrous do not come from mechanical failure due to the power increases. Since nitrous allows a much denser charge into the cylinder, it dramatically increases cylinder pressures. The increased pressure and temperature can cause problems such as melting the piston or valves. It may also crack or warp the piston or head and cause pre-ignition due to uneven heating. Automotive-grade liquid nitrous oxide differs slightly from medical-grade nitrous oxide. A small amount of sulfur dioxide, SO2, is added to prevent substance abuse. Multiple washes through a base can remove this, decreasing the corrosive properties observed when SO2 is further oxidized during combustion into sulfuric acid, making emissions cleaner. Aerosol propellant, the gas is approved for use as a food additive, specifically as an aerosol spray propellant. Its most common uses in this context are in aerosol whipped cream canisters, cooking sprays, and as an inert gas used to displace oxygen, to inhibit bacterial growth, when filling packages of potato chips and other similar snack foods. The gas is extremely soluble in fatty compounds. In aerosol whipped cream, it is dissolved in the fatty cream until it leaves the can, when it becomes gaseous and thus creates foam. Used in this way, it produces whipped cream 4 times the volume of the liquid, whereas whipping air into cream only produces twice the volume. If air were used as a propellant, oxygen would accelerate rancidification of the butterfat. Nitrous oxide inhibits such degradation. Carbon dioxide cannot be used for whipped cream because it is acidic in water, which would curdle the cream and give it a seltzer-like sparkling sensation. However, the whipped cream produced with nitrous oxide is unstable and will return to a more liquid state within half an hour to 1 hour. Thus, the method is not suitable for decorating food that will not be immediately served. Similarly, cooking spray, which is made from various types of oils combined with lecithin, may use nitrous oxide as a propellant. Other propellants used in cooking spray include food-grade alcohol and propane. Users of nitrous oxide often obtain it from whipped cream dispensers that use nitrous oxide as a propellant, for recreational use as a euphoria-inducing inhalant drug. It is not harmful in small doses, but risks due to lack of oxygen do exist. Medicine. Nitrous oxide has been used for anesthesia in dentistry since December 1844, where Horace Wells made the first 12 dental operations with the gas in Hartford. Its debut as a generally accepted method, however, came in 1863, when Gardner Quincy Colton introduced it more broadly at all the Colton Dental Association clinics, that he founded in New Haven in New York City. The first devices used in dentistry to administer the gas, known as nitrous oxide inhalers, were designed in a very simple way with the gas stored and breathed through a breathing bag made of rubber cloth, without a scavenger system and flowmeter, and with no addition of oxygen air. Today these simple and somewhat unreliable inhalers have been replaced by the more modern relative analgesia machine, which is an automated machine designed to deliver a precisely dosed and breath-actuated flow of nitrous oxide mixed with oxygen, for the patient to inhale safely. The machine used in dentistry is designed as a simplified version of the larger anesthetic machine used by hospitals, as it doesn't feature the additional anesthetic vaporizer and medical ventilator. The purpose of the machine allows for a simpler design, as it only delivers a mixture of nitrous oxide and oxygen for the patient to inhale, in order to depress the feeling of pain while keeping the patient in a conscious state. Relative analgesia machines typically feature a constant supply flowmeter, which allow the proportion of nitrous oxide and the combined gas flow rate to be individually adjusted. The gas is administered by dentists through a demand valve inhaler over the nose, which will only release gas when the patient inhales through the nose. Because nitrous oxide is minimally metabolized in humans, it retains its potency when exhaled into the room by the patient, and can pose an intoxicating and prolonged exposure hazard to the clinic staff if the room is poorly ventilated. Where nitrous oxide is administered, a continuous flow fresh air ventilation system or nitrous scavenger system is used to prevent a waste gas build-up. Hospitals administer nitrous oxide as one of the anesthetic drugs delivered by anesthetic machines. Nitrous oxide is a weak general anesthetic, and so is generally not used alone in general anesthesia. In general anesthesia it is used as a carrier gas in a 2-to-1 ratio with oxygen for more powerful general anesthetic drugs such as sevoflurane or desflurane. It has a minimum alveolar concentration of 105% and a blood gas partition coefficient of 0.46. The medical-grade gas tanks, with the trade name Entonox and Nitronox, contain a mixture with 50%. But this will normally be diluted to a lower percentage upon the operational delivery to the patient. Inhalation of nitrous oxide is frequently used to relieve pain associated with childbirth, trauma, oral surgery, and acute coronary syndrome. Its use during labor has been shown to be a safe and effective aid for women wanting to give birth without an epidural. Its use for acute coronary syndrome is of unknown benefit. In Britain and Canada, Entonox and Nitronox are commonly used by ambulance crews as a rapid and highly effective analgesic gas. Nitrous oxide has been shown to be effective in treating a number of addictions, including alcohol withdrawal. Nitrous oxide is also gaining interest as a substitute gas for carbon dioxide in laparoscopic surgery. It has been found to be as safe as carbon dioxide with better pain relief. Recreational use. Nitrous oxide can cause analgesia, depersonalization, derealization, dizziness, euphoria, and some sound distortion. Research has also found that it increases suggestibility and imagination. Inhalation of nitrous oxide for recreational use, with the purpose of causing euphoria and/or slight hallucinations, began as a phenomenon for the British upper class in 1799, known as laughing gas parties. Until at least 1863, a low availability of equipment to produce the gas, combined with the low usage of the gas for medical purposes, meant it was a relatively rare phenomenon that mainly happened among students at medical universities. When equipment became more widely available for dentistry and hospitals, most countries also restricted the legal access to buy pure nitrous oxide gas cylinders to those sectors. As only medical staff and dentists today are legally allowed to buy the pure gas, the recreational use is also believed to be somewhat limited. A Consumers Union report from 1972, however, found that the use of the gas for recreational purpose was, then still taking place, based upon reports of its use in Maryland, 1971, Vancouver 1972, and a survey made by Dr. Edward J. Lynn of its non-medical use in Michigan, 1970. It was not uncommon, in the interviews, to hear from individuals who had been to parties where a professional had provided nitrous oxide. There also were those who work in restaurants who use the N2O stored in tanks for the preparation of whipped cream. Reports were received from people who used the gas contained in aerosol cans, both of food and non-food products. At a recent rock festival, nitrous oxide was widely sold for 25 cents a balloon. Contact was made with a mystical religious group that used the gas to accelerate arriving at their transcendental meditative state of choice. Although a few, more sophisticated users employed nitrous oxide oxygen mixes with elaborate equipment, most users used balloons or plastic bags. They either held a breath of N2O or rebreathed the gas. There were no adverse effects reported in the more than 100 individuals surveyed. In Australia, nitrous oxide bulbs are known as nangs, possibly derived from the sound distortion perceived by consumers. In the United Kingdom, recreational use of nitrous oxide has been referred to as hippie crack. Mechanism of action: the pharmacological mechanism of action of N2O in medicine is not fully known. However, it has been shown to directly modulate a broad range of ligand-gated ion channels, and this likely plays a major role in many of its effects. It moderately blocks NMDA and I2 subunit containing NACH channels, weakly inhibits AMPA, kainate, GABAC, and 5-HT3 receptors, and slightly potentiates GABAA and glycine receptors. It has also been shown to activate 2-pore domain K+ channels. While N2O affects quite a few ion channels, its anesthetic, hallucinogenic, and euphoric effects are likely caused predominantly or fully via inhibition of NMDAR-mediated currents. In addition to its effects on ion channels, N2O may act to imitate nitric oxide in the central nervous system, and this may be related to its analgesic and anxiolytic properties. Anxiolytic effect: in behavioral tests of anxiety, a low dose of N2O is an effective anxiolytic, and this anti-anxiety effect is associated with enhanced activity of GABAA receptors, as it is partially reversed by benzodiazepine receptor antagonists. Mirroring this, animals which have developed tolerance to the anxiolytic effects of benzodiazepines are partially tolerant to N2O. Indeed, in humans given 30% N2O, benzodiazepine receptor antagonists reduced the subjective reports of feeling high, but did not alter psychomotor performance, in human clinical studies. Analgesic effect: the analgesic effects of N2O are linked to the interaction between the endogenous opioid system and the descending noradrenergic system. When animals are given morphine chronically, they develop tolerance to its pain-killing effects, and this also renders the animals tolerant to the analgesic effects of N2O. Administration of antibodies which bind and block the activity of some endogenous opioids also block the antinociceptive effects of N2O. Drugs which inhibit the breakdown of endogenous opioids also potentiate the antinociceptive effects of N2O. Several experiments have shown that opioid receptor antagonists applied directly to the brain block the antinociceptive effects of N2O, but these drugs have no effect when injected into the spinal cord. Conversely, I+ or -2 adrenoceptor antagonists block the pain-reducing effects of N2O when given directly to the spinal cord, but not when applied directly to the brain. Indeed, I+ or -2B adrenoceptor knockout mice or animals depleted in norepinephrine are nearly completely resistant to the antinociceptive effects of N2O. Apparently N2O-induced release of endogenous opioids causes disinhibition of brainstem noradrenergic neurons, which release norepinephrine into the spinal cord and inhibit pain signaling. Exactly how N2O causes the release of endogenous opioid peptides is still uncertain. Euphoric effect: in rats, N2O stimulates the mesolimbic reward pathway via inducing dopamine release and activating dopaminergic neurons in the ventral tegmental area and nucleus accumbens, presumably through antagonization of NMDA receptors localized in the system. This action has been implicated in its euphoric effects, and notably, appears to augment its analgesic properties as well. However, it is remarkable that in mice, N2O blocks amphetamine-induced carrier-mediated dopamine release in the nucleus accumbens and behavioral sensitization, abolishes the conditioned place preference of cocaine and morphine, and does not produce reinforcing effects of its own. Studies on CPP of N2O in rats is mixed, consisting of reinforcement, aversion, and no change. In contrast, it is a positive reinforcer in squirrel monkeys, and is well known as a drug of abuse in humans. These discrepancies in response to N2O may reflect species variation or methodological differences. Though, it is noteworthy that in human clinical studies, N2O was found to produce mixed responses similarly to rats, reflecting high subjective individual variability. Neurotoxicity and neuroprotection: like other NMDA antagonists, N2O was suggested to produce neurotoxicity in the form of Olney's lesions in rodents upon prolonged exposure. However, new research has arisen suggesting that Olney's lesions do not occur in humans, and similar drugs like ketamine are now believed not to be acutely neurotoxic. It has been argued that, because N2O has a very short duration under normal circumstances, it is less likely to be neurotoxic than other NMDA antagonists. Indeed, in rodents, short-term exposure results in only mild injury that is rapidly reversible, and permanent neuronal death only occurs after constant and sustained exposure. Nitrous oxide may also cause neurotoxicity after extended exposure because of hypoxia. This is especially true of non-medical formulations such as whipped cream chargers, which are not necessarily mixed with oxygen. Additionally, nitrous oxide depletes vitamin B12 levels. This can cause serious neurotoxicity with even acute use if the user has pre-existing vitamin B12 deficiency. Nitrous oxide is also neuroprotective, inhibiting glutamate-induced excitotoxicity. Safety. The major safety hazards of nitrous oxide come from the fact that it is a compressed liquefied gas, an asphyxiation risk, and a dissociative anesthetic. Exposure to nitrous oxide causes short-term decreases in mental performance, audio-visual ability, and manual dexterity. Long-term exposure can cause vitamin B12 deficiency, numbness, reproductive side effects, and other problems. The National Institute for Occupational Safety and Health recommends that workers' exposure to nitrous oxide should be controlled during the administration of anesthetic gas in medical, dental, and veterinary operators. Chemical physical. At room temperature the saturated vapor pressure is 58.5 bar, rising up to 72.45 bar at 36.4 aa degree Celsius the critical temperature. The pressure curve is thus unusually sensitive to temperature. Liquid nitrous oxide acts as a good solvent for many organic compounds. Liquid mixtures may form shock-sensitive explosives. As with many strong oxidizers, contamination of parts with fuels have been implicated in rocketry accidents, where small quantities of nitrous fuel mixtures explode due to water hammer-like effects. Some common building materials such as stainless steel and aluminium can act as fuels with strong oxidizers such as nitrous oxide, as can contaminants, which can ignite due to adiabatic compression. There have also been accidents where nitrous oxide decomposition in plumbing has led to the explosion of large tanks. Biological. Nitrous oxide inactivates the cobalamin form of vitamin B12 by oxidation. Symptoms of vitamin B12 deficiency, including sensory neuropathy, myelopathy, and encephalopathy, can occur within days or weeks of exposure to nitrous oxide anesthesia in people with subclinical vitamin B12 deficiency. Symptoms are treated with high doses of vitamin B12, but recovery can be slow and incomplete. People with normal vitamin B12 levels have stores to make the effects of nitrous oxide insignificant, unless exposure is repeated and prolonged. Vitamin B12 levels should be checked in people with risk factors for vitamin B12 deficiency prior to using nitrous oxide anesthesia. A study of workers and several experimental animal studies indicate that adverse reproductive effects for pregnant females may also result from chronic exposure to nitrous oxide. Environmental. N2O is a greenhouse gas with tremendous global warming potential. When compared to carbon dioxide, CO2, N2O has 298 times the ability per molecule of gas to trap heat in the atmosphere. N2O is produced naturally in the soil during the microbial processes of nitrification and denitrification. The United States of America signed and ratified the United Nations Framework Convention on Climate Change in 1992, agreeing to inventory and assess the various sources of greenhouse gases that contribute to climate change. The agreement requires parties to develop, periodically update, publish and make available national inventories of anthropogenic emissions by sources and removals by sinks of all greenhouse gases not controlled by the Montreal Protocol, using comparable methodologies. In response to this agreement, the U.S. is obligated to inventory anthropogenic emissions by sources and sinks, of which agriculture is a key contributor. In 2008, Agriculture contributed 6.1% of the total U.S. greenhouse gas emissions, and cropland contributed nearly 69% of total direct nitrous oxide, N2O, emissions. Additionally, estimated emissions from agricultural soils were 6% higher in 2008 than 1990. According to 2006 data from the United States Environmental Protection Agency, industrial sources make up only about 20% of all anthropogenic sources, and include the production of nylon, and the burning of fossil fuel in internal combustion engines. Human activity is thought to account for 30%. Tropical soils and oceanic release account for 70%. However, a 2008 study by Nobel laureate Paul Crutzen suggests that the amount of nitrous oxide release attributable to agricultural nitrate fertilizers has been seriously underestimated, most of which would presumably come under soil and oceanic release in the Environmental Protection Agency data. Atmospheric levels have risen by more than 15% since 1750. Nitrous oxide also causes ozone depletion. A new study suggests that N2O emission currently is the single most important ozone-depleting substance emission and is expected to remain the largest throughout the 21st century. Production. Nitrous oxide is most commonly prepared by careful heating of ammonium nitrate, which decomposes into nitrous oxide and water vapor. The addition of various phosphates favors formation of a purer gas at slightly lower temperatures. One of the earliest commercial producers was George Poe in Trenton, New Jersey. NH4NO, 3 or 2 hours, 2O plus N2O. This reaction occurs between 170 and 240 AA degrees Celsius, temperatures where ammonium nitrate is a moderately sensitive explosive and a very powerful oxidizer. Above 240 AA degrees Celsius, the exothermic reaction may accelerate to the point of detonation, so the mixture must be cooled to avoid such a disaster. Superheated steam is used to reach reaction temperature in some turnkey production plants. Downstream, the hot, corrosive mixture of gases must be cooled to condense the steam, and filtered to remove higher oxides of nitrogen. Ammonium nitrate smoke, as an extremely persistent colloid, will also have to be removed. The cleanup is often done in a train of 3 gas washes, namely base, acid and base again. Any significant amounts of nitric oxide may not necessarily be absorbed directly by the base washes. The nitric oxide impurity is sometimes chelated out with ferrous sulfate, reduced with iron metal, or oxidized and absorbed in base as a higher oxide. The first base wash may react out much of the ammonium nitrate smoke. However, this reaction generates ammonia gas, which may have to be absorbed in the acid wash. Other routes, the direct oxidation of ammonia may someday rival the aforementioned method of ammonium nitrate pyrolysis. This capital-intensive process, which originates in Japan, uses a manganese dioxide bismuth oxide catalyst, 2NH, 3 plus 2O, 2N, 2O plus 3 hours, 2O, higher oxides of nitrogen are formed as impurities. In comparison, uncatalyzed ammonia oxidation goes primarily to N2 and H2O. Nitrous oxide can be made by heating a solution of sulfamic acid and nitric acid. Many gases are made this way in Bulgaria. HNO, 3 plus NH, 2SO, 3 hours En, 2O plus H, 2SO, 4 plus H, 2O. There is no explosive hazard in this reaction if the mixing rate is controlled. However, as usual, toxic higher oxides of nitrogen are formed. Nitrous oxide is produced in large volumes as a byproduct in the synthesis of adipic acid, one of the 2 reactants used in nylon manufacture. This might become a major commercial source, but will require the removal of higher oxides of nitrogen and organic impurities. Currently much of the gas is decomposed before release for environmental protection. Hydroxylammonium chloride can react with sodium nitrite to produce N2O as well, NH, 3OH plus Cla plus NaNO, 2N, 2O plus NaCl plus 2 hours, 2O. If the nitrite is added to the hydroxylamine solution, the only remaining byproduct is salt water. However, if the hydroxylamine solution is added to the nitrite solution, then toxic higher oxides of nitrogen are also formed. Also, HNO3 can be reduced to N2O by SnCl, 2 and HCl mixture, 2HNO3 plus 8HCl plus 4SnCl, 2 of 5 hours, 2O plus 4SnCl, 4 plus N2O. Natural production of N2O occurs through the process of denitrification in oxygen-poor soils and marine environments, in which denitrifying bacteria respire NO3. High-pore nitrous acid decomposes to N2O and water with a half-life of 16 days at 25 AA degrees Celsius at penthouse 1 to 3. H2N2O2 H2O plus N2O, as this reaction is not reversible, N2O should not be considered as the anhydride of H2N2O2. Soil. Of the entire anthropogenic N2O emission, 5.7 teragrams N2O per year, agricultural soils provide 3.5 teragrams N2O per year. Nitrous oxide is produced naturally in the soil during the microbial processes of nitrification, denitrification, nitrifier denitrification and others, aerobic autotrophic nitrification, the stepwise oxidation of ammonia, NH3, to nitrite, NO2, and to nitrate, NO3, anaerobic heterotrophic denitrification, the stepwise reduction of NO3 to NO2, nitric oxide, N2O and ultimately N2, where facultative anaerobe bacteria use NO3 as an electron acceptor in the respiration of organic material in the condition of insufficient oxygen, O2, and nitrifier denitrification, which is carried out by autotrophic NH3 oxidizing bacteria and the pathway whereby ammonia, NH3, is oxidized to nitrite, NO2, followed by the reduction of NO2 to nitric oxide, N2O and molecular nitrogen, N2. Other N2O production mechanisms include heterotrophic nitrification, aerobic denitrification by the same heterotrophic nitrifiers, fungal denitrification, and non-biological process chemodenitrification. Soil N2O emissions are reported to be controlled by soil chemical and physical properties such as the availability of mineral N, soil pH, organic matter availability, and soil type, and climate-related soil properties such as soil temperature and soil water content. Properties and reactions. Nitrous oxide is a colourless, non-toxic gas with a faint, sweet odour. Nitrous oxide supports combustion by releasing the dipolar bonded oxygen radical, name. Thus it can relight a glowing splint. N2O is inert at room temperature and has few reactions. At elevated temperatures, its reactivity increases. For example, nitrous oxide reacts with NaN2 at 460 K to give NaN3, 2 NaN2 plus N2O and NaN3 plus NaO plus NH3. The above reaction is actually the route adopted by the commercial chemical industry to produce acid salts, which are used as detonators. Occurrence. Nitrous oxide is emitted by bacteria in soils and oceans, and is thus a part of Earth's atmosphere. Agriculture is the main source of human-produced nitrous oxide. Cultivating soil, the use of nitrogen fertilizers, and animal waste handling can all stimulate naturally occurring bacteria to produce more nitrous oxide. The livestock sector produces 65% of human-related nitrous oxide. Industrial sources make up only about 20% of all anthropogenic sources, and include the production of nylon, and the burning of fossil fuel in internal combustion engines. Human activity is thought to account for 30%. Tropical soils and oceanic release account for 70%. Nitrous oxide reacts with ozone in the stratosphere. Nitrous oxide is the main naturally occurring regulator of stratospheric ozone. Nitrous oxide is a major greenhouse gas. Considered over a 100-year period, it has 298 times more impact per unit weight than carbon dioxide. Thus, despite its low concentration, nitrous oxide is the fourth largest contributor to these greenhouse gases. It ranks behind water vapor, carbon dioxide, and methane. Control of nitrous oxide is part of efforts to curb greenhouse gas emissions. History. The gas was first synthesized by English natural philosopher and chemist Joseph Priestley in 1772, who called it phlogisticated nitrous air. Priestley published his discovery in the book Experiments and Observations on Different Kinds of Air, where he described how to produce the preparation of nitrous air diminished, by heating iron filings dampened with nitric acid. Early use. The first important use of nitrous oxide was made possible by Thomas Beddoes and James Watt, who worked together to publish the book Considerations on the Medical Use and on the Production of Factitious Airs. This book was important for two reasons. First, James Watt had invented a novel machine to produce factitious airs, and a novel breathing apparatus to inhale the gas. Second, the book also presented the new medical theories by Thomas Beddoes, that tuberculosis and other lung diseases could be treated by inhalation of factitious airs. The machine to produce factitious airs had three parts: a furnace to burn the needed material, a vessel with water where the produced gas passed through in a spiral pipe, and finally the gas cylinder with a gasometer where the gas produced, air, could be tapped into portable airbags. The breathing apparatus consisted of one of the portable airbags connected with a tube to a mouthpiece. With this new equipment being engineered and produced by 1794, the way was paved for clinical trials, which began when Thomas Beddoes in 1798 established the Pneumatic Institution for Relieving Diseases by Medical Airs in Hotwells. In the basement of the building, a large-scale machine was producing the gases under the supervision of a young Humphrey Davy, who was encouraged to experiment with new gases for patients to inhale. The first important work of Davy was examination of the nitrous oxide, and the publication of his results in the book, Researches, Chemical and Philosophical. In that publication, Davy notes the analgesic effect of nitrous oxide at page 465 and its potential to be used for surgical operations at page 556. Despite Davy's discovery that inhalation of nitrous oxide could relieve a conscious person from pain, another 44 years elapsed before doctors attempted to use it for anesthesia. The use of nitrous oxide as a recreational drug at laughing gas parties, primarily arranged for the British upper class, became an immediate success beginning in 1799. While the effects of the gas generally make the user appear stuporous, dreamy and sedated, some people also get the giggles in a state of euphoria, and frequently erupt in laughter. Anesthetic use. The first time nitrous oxide was used as an anesthetic drug in the treatment of a patient was when dentist Horace Wells, with assistance by Gardner Quincy Colton and John Mankey Riggs, demonstrated insensitivity to pain from a dental extraction on December 11, 1844. In the following weeks, Wells treated the first 12-15 patients with nitrous oxide in Hartford, and according to his own record only failed in 2 cases. In spite of these convincing results being reported by Wells to the Medical Society in Boston already in December 1844, this new method was not immediately adopted by other dentists. The reason for this was most likely that Wells, in January 1845 at his first public demonstration to the medical faculty in Boston, had been partly unsuccessful, leaving his colleagues doubtful regarding its efficacy and safety. The method did not come into general use until 1863, when Gardner Quincy Colton successfully started to use it in all his Colton Dental Association clinics, that he had just established in New Haven in New York City. Over the following 3 years, Colton and his associates successfully administered nitrous oxide to more than 25,000 patients. Today, nitrous oxide is used in dentistry as an anxiolytic, as an adjunct to local anesthetic. However, nitrous oxide was not found to be a strong enough anesthetic for use in major surgery in hospital settings. Being a stronger and more potent anesthetic, sulfuric ether was instead demonstrated and accepted for use in October 1846, along with chloroform in 1847. When Joseph Thomas Clover invented the gas ether inhaler in 1876, it however became a common practice at hospitals to initiate all anesthetic treatments with a mild flow of nitrous oxide, and then gradually increase the anesthesia with a stronger ether chloroform. Clover's gas ether inhaler was designed to supply the patient with nitrous oxide and ether at the same time, with the exact mixture being controlled by the operator of the device. It remained in use by many hospitals until the 1930s. Although hospitals today are using a more advanced anesthetic machine, these machines still use the same principle launched with Clover's gas ether inhaler, to initiate the anesthesia with nitrous oxide, before the administration of a more powerful anesthetic. Legality. In the United States, possession of nitrous oxide is legal under federal law and is not subject to DEA purview. It is, however, regulated by the Food and Drug Administration under the Food, Drug and Cosmetics Act. Prosecution is possible under its misbranding clauses, prohibiting the sale or distribution of nitrous oxide for the purpose of human consumption. Many states have laws regulating the possession, sale, and distribution of nitrous oxide. Such laws usually ban distribution to minors or limit the amount of nitrous oxide that may be sold without special license. For example, in the state of California, possession for recreational use is prohibited and qualifies as a misdemeanor. In New Zealand, the Ministry of Health has warned that nitrous oxide is a prescription medicine, and its sale or possession without a prescription is an offence under the Medicines Act. This statement would seemingly prohibit all non-medicinal uses of the chemical, though it is implied that only recreational use will be legally targeted. In India, for general anesthesia purposes, nitrous oxide is available as nitrous oxide IP. India's gas cylinder rules permit the transfer of gas from one cylinder to another for breathing purposes. This law benefits remote hospitals, which would otherwise suffer as a result of India's geographic immensity. Nitrous oxide IP is transferred from bulk cylinders to smaller pin-indexed valve cylinders, which are then connected to the yoke assembly of Boyle's machines. Because India's Food and Drug Authority rules state that transferring a drug from one container to another is equivalent to manufacturing, anyone found doing so must possess a drug manufacturing license. See also, whipped cream charger, diffusion hypoxia, nitrous oxide fuel blend, references. External links, Occupational Safety and Health Guideline for Nitrous Oxide, Paul Crutzen interview Freeview video of Paul Crutzen Nobel laureate for his work on decomposition of ozone talking to Harry Kroto Nobel laureate by the Vega Science Trust. National Pollutant Inventory Oxide of nitrogen fact sheet, National Institute for Occupational Safety and Health Nitrous oxide, CDC NIOSH Pocket Guide to Chemical Hazards Nitrous oxide FAQ, Aeroid article on nitrous oxide fingered as monster ozone slayer, Science News, Dental Fear Central article on the use of nitrous oxide in dentistry.